our last topic on the section number 1, I wanted to show you why temperature is not the same as heat. And I know we use it very interchange. We exchange that value, like we say temperature is that of heat and hot is cold and low temperature means it's cold, etc. But in engineering, and especially in thermodynamics, we cannot make that luxury. We cannot say that temperature is the same as heat, and we're going to see this why. So let me give you a little intro. What has more heat energy? A boiling pot of water at 100 Celsius, which let's say probably is 1 kilogram of water, or an iceberg at 0 Celsius, but you know it's probably, I don't know, 100 ton. Just think about it, guys. What has more heat energy? Let me continue. Before going there, I'm going to go back, of course, but I want to give you or show you the temperature is an intensive property, does not depend on the quantity, and the heat does depends on the mass quantity. That's why I told you here, this is probably 1 ton, and this is probably 1 kilogram. Once again, temperature is the average movement of molecules, and heat is the energy needed to achieve that temperature. Okay, so once again, what is going to take you more if you wanted to cool down this pot or cool down this iceberg, or backwards? You have a lot of mass, guys, so changing the state of this will cost you a lot of energy, heat energy. You will need to heat it a lot. And changing that of boiling water, even though it's high temperature, well, it's not that a problem because it's a little bit, it's only 1 kilogram. Maybe we can add 10 kilograms of ice and it will be okay. But if you wanted to add, I don't know, maybe 10 kilograms of steam to this iceberg, you know, because it's huge, it's 100 or 1000 ton, well, you will need a lot more. So hopefully you're getting the idea of heat. What's heat? Is energy content. And actually, I want to give you this definition of heat. Probably you've seen it before. It's at constant pressure. Q equals the mass times the specific or all the heat that can get that material times the change in temperature. So as you can see, Q depends on mass, but temperature does not. This is, let's say, one number. But you can see Q here depends with mass, and temperature only depends with the average velocity movement. Let me give you more examples so you can get a clear idea on why it's not the same temperature and heat. How much heat would you need to boil the ocean, whole ocean? Well, you have a lot of water, and probably you go there and you see that there's a sun, and you know that the sun gives a lot of heat energy. And why does not boil at all? Well, of course, because it's a lot. It's a lot of mass. Even though it's at maybe 25 Celsius, it is a lot. So increasing this 25 to 100 Celsius implies a lot of energy. So see how come I'm using temperature to know how much heat energy. But not only that, I also know that there is a lot of mass. So heat, you're seeing probably now that heat implies mass and a temperature change. Now, how much heat is needed to boil a cup of coffee? That will be way easier, even though I'm also, let's say it's cold, it's 25 Celsius in ambient, I let it in my table and I want to reheat it. I want to almost vaporize it. I love super hot coffee. So let's say how much? You will definitely say that this is possible, yes, because it's not that much mass. The heat needed will be a little bit or a lot less than that boiling of the ocean. Even though we're talking about almost the same substance, which is water, you need way much energy here than here to achieve the same temperature. This one is a little bit more abstract, but if you like to drink Coke with ice or any drink, alcoholic drink or water with ice, you will get it. What will decrease the temperature of your drink? I'm talking now about super cold, or I'm talking about low temperatures, not about heat. 1 cube of ice at -2 Celsius, or 5 cubes of ice at 0 Celsius. So if I wanted to go, like if I love low temperatures, I should choose this one, because maybe this is going to get to -1 Celsius. And even though I have a lot of ice cube, this will never go down. The minimum will be 0 Celsius. And I know that maybe this is not a lot of difference. Probably I should have chosen -12 Celsius. And then I will be speaking about -10 Celsius versus 0 Celsius, which of course makes a lot of difference. 0 Celsius is cold, -10 Celsius is super cold. Hopefully you're getting now the idea once again. And I'm talking about number of cubes, because you know that the more cubes you add, the faster and the lower temperature you get. And one last example before going. What is more dangerous to your health? An ocean, a huge amount of mass, that is maybe at 30 Celsius. And let's say you are in the beach and you want to go inside the ocean, but you never heard your mom tell you, hey, it's 30 Celsius, don't go in, it's going to burn you. Even though it's a lot of mass, actually you will need a lot of energy to move that. But if you're talking about steam, a small amount of mass, maybe, I don't know, one cup, which is about 250 milliliters, or about, I think, 8 ounces, liquid ounces, at 120 Celsius, well, of course, you know this is way more dangerous. You can even get burned. But why, if it's only 1 cup, and we're speaking about here about a huge amount of ocean? Now you're starting to get the idea of temperature, high temperature, low temperatures, high mass, low mass. What I was telling you, there are many cases in which you have a small mass and a low temperature. You have a large mass and a high temperature. This is actually a very interesting case. Large mass and high temperature, oh, this should say low, and small mass, large or high temperature. This is also, one example will be this cup, 1 cup being turned into steam. This will be maybe a star or a sun. Small mass, low temperature will be 1 cube of ice. And large mass, low temperature will be, I don't know, maybe the ocean, 25 Celsius. It's a low temperature, but it's huge mass. So probably you're getting the idea of, or hopefully guys, now you get more the idea of temperature and heat and why they are not the same. So in the next video, we're going to continue with section number 2, which is force, weight, and pressure. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.